right? It says a six-sided die is rolled. Find each probability first, decide if they're mutually exclusive or not, and then the probability that the number rolled is less than 3 and greater than 5. So these are just one die. You don't need that yet, okay? The first one says the probability that the number roll is less than 3 or greater than 5. So can a number be less than 3 and greater than 5? Have a good day, guys.
Thank you.
Can a number be less than 3 and greater than 5? No. So are these mutually exclusive or not mutually exclusive? They are mutually exclusive. Mutually exclusive means they can't be both things. It can't be less than 3 and greater than 5, right?
So if there's an and, it's not mutually exclusive?
No, if it's an or question, which is what this is, you have to figure out if they are mutually exclusive. Mutually exclusive means they cannot be the same. They can't be both less than 3 and greater than 5, right? Think about it. Less than 3 is what? On a die. 1 and 2, right? What's greater than 5? 6. They can't be both of those things. If they cannot be both, they're mutually exclusive. If they can be both, that's when it's not mutually exclusive. So because these are mutually exclusive, you just find the probability that it's less than 3, and then you add it to the probability that it's greater than 5. So less than 3, we said there's 2 out of the 6. And then greater than 5, we said there's 1 out of the 6. So you can either simplify, but then you're going to have to find a least common denominator anyways, or keep them the way they are. I'd get 3 out of 6, which is 1/2. You could have also just count your die on that one. Okay. 2 says the probability of rolling a number greater than 4 or even. So can a number be greater than 4 and also even? Yes, so this is not mutually exclusive. So we find the probability that it's greater than 4 plus the probability that it's even, and we subtract from it the probability that it is both greater than 4 and even.
How did you know we could do that?
Because they're not mutually exclusive. So when you see the word or in your word problem, you have to figure out if it's mutually exclusive or not. These are not mutually exclusive.
What does mutually exclusive mean again?
That they can mutually exclusive means they cannot be both. It cannot be.
Oh, it's like when it overlaps.
If it's an overlap, it is not mutually exclusive, which is what this is.
And a face, like
Correct. Correct. So what's the probability that it's greater than 4? 2 out of the 6, right? That would be the 5 and the 6. What's the probability that it's even? 2, 4, and 6, so 3 out of the 6. And then what's the probability that it's even and greater than 4? 1 out of 6, just that side 6, right? So I'd get 5 minus 1. This is 4/6, or 2/3. So when you see the word or in your original question, you have to figure out, is it mutually exclusive or not? Yeah, sure. So all of these are ors, okay? A card is randomly selected from a standard deck of 52 cards. Find the probability of the given event. So if you still need your deck of cards, obviously you can pull that picture in, but by test time, you want to make sure that you know the deck of cards because it won't be given on your test. Put in my favorites. Yeah. All right, so this one says number 3, selecting a 5 or a face card. Again, the word or there means, hey, look and see if it's mutually exclusive or not. So can a card be both a 5 and a face card? No, so these are mutually exclusive. So we said these are mutually exclusive, which means we need to find the probability of picking a 5 and add it to the probability of getting a face card. How many 5s are there? 4 out of my total, which is 52. How many face cards are there? 12 out of 52. You can actually simplify these both, or you can add them and simplify them. It doesn't matter. You'd get 4 out of 13.
What if you subtract? Are they mutually exclusive? What do you
You never subtract.
But no, what do you subtract the ones that like overlap?
There's no 5 that's a face card. That's only if they're not mutually exclusive, right? Yeah. All right, 4 face card or a diamond. So can it be both a face card and a diamond? Yes, this is when it's mutually exclusive, or not mutually exclusive. So we do probability of face card plus probability of diamond minus the probability of a diamond that's a face card. So we just said there are 12 face cards, 12 out of 52. How many diamonds? 13 out of 52. How many diamonds that are face cards? 3 out of 52.
For reference, in all the problems that you give us, is ace going to count as a face card?
As a face card, it will never count as a face card. It has to have a face on it. So only jacks, queens, king.
Okay.
Yeah. The only thing that will change with ace is if it's high or low, and that it will be explicitly stated. If it's asking for a number, like is it greater than 5 or less than 5, and ace would be blank. All right, so now we're doing, so this is 25 minus 3, that's 22 over 52, which is 11 out of 26. All right, then it says select an ace or a 9. Again, the word or is there, so can it be both an ace and a 9? No, this is mutually exclusive. Probability of an ace, how many aces are there? 4 out of 52. Probability of a 9, 4 out of 52. So 8 out of 52, or 2/13. And a 10 or a diamond, can it be both a 10 and a diamond? Yes, this is not mutually exclusive. So the probability it's a 10 is what? 4 out of 52. A diamond? 13 out of 52. A 10, that's a diamond. 1. So this is 17 minus 1, that's 16 out of 52, or 4/13. All right, so the good news is we kind of got our feet wet with this last week, but we're going to finish out 8-6, which is finding the probabilities of independent and dependent events. So we talked about independent events last week, and now we're going to add independent events. So something called the complement of an event can be used in certain scenarios to make things easier. You don't have to use a complement. I'm going to teach you obviously how to use it, but sometimes you want to use it in probability and sometimes it's because it will make your set easier. So it consists of all the outcomes that are not in the event. So if I said to you that the probability of getting A is 5 out of 11, the probability of not getting A would be what? 6 out of 11. That's a complement. So the complement is what you would not get, okay? What you don't want to get. Sometimes what you don't want is more than what you do want, and sometimes what you don't want is less than what you do want. When it's less, it's actually easier sometimes to find what you don't want and then just subtract it from 1, and that's what this complement is. So the notation for it is like this, and that's A bar. It's literally read as A bar. So to find the complement to A, we do 1 minus A bar, or the other way around. A bar would be 1 minus A.
So A bar is like the complement.
The complement, yep. It'd be 1 minus whatever the probability is of that you're looking for, okay? The reason you would use it is something like this. So here's our 6-sided die again, okay? It says when 2 6-sided die are rolled, find the probability of each event. In A, it says the sum is not 6. So if I wanted to find where the sum is not 6 without using the complement, I would have to count all the boxes that were not 6. You see that? Yes? If I use the complement, then I can count the number of boxes that are 6 and then subtract it from 1.
But we're not going to have that sheet on the test, right?
This, no.
So would we have to memorize?
I'll teach you how to fill it in, but it's just a pattern. You start at 2 and then you go up in each direction. It's increasing by 1 every time. Yeah. So if I were to, again, let's say I said without using the complement, the sum is not 6. I'd have to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. It would be 31 out of the total amount, which is 6 times 6 or 36. That's the answer, okay? But sometimes it's faster to try to find what you don't want and then subtract it from 1. So let's say the sum is 6. It's 1, 2, 3, 4, 5. There's 5 of them. 5 out of 36 is 6. So I would do 1 minus that. And I get 31 over 36. So you don't have to do it that way. You get to choose. Sometimes it is faster to find what you don't want and subtract it from 1 than it is to find what you do want. It was 1 minus 5 over 36, but then I changed it to 36 over 36. So now the sum is less than or equal to 9. Again, I want you to, this time just practice it doing the complement. You don't have to do it this way. But if it's less than or equal to 9, how many numbers are there more numbers less than or equal to 9 or more numbers greater than 9?
Greater than 9.
Less than, right? I have to count 9 in all these numbers, right? Or I say, okay, what's greater than 9? 1, 2, 3, 4, 5, 6. There's only 6. So greater than 9 is 6 out of 36. Just subtract that from the 36 over 36.
Doesn't it want equal to 9 too, so we should add the ones that are equal to 9?
In what you want, right? But not if you're using the complement. If you're using the complement, you're saying what's the opposite of this? It's that it would be greater than 9. So I only include the 10, 11, and 12. So then this would reduce to what goes into both of those?
They're asking for some, not just like getting something that is less or greater.
But this box is the sum. This is 1 plus 1, 2 plus 1. The box did the sum for you. Yeah.
So it's much easier.
Yep, than trying to figure it all out. All right, now we go independent, okay? So we talked about independent last week, right? Independent is that the occurrence of one thing does not affect the occurrence of the other. These are all for and statements. So at the end, I'm going to set up a little chart for you, the and, the or, and then what you have to do for each. But we already talked about the or. The or was what we just did the warm-up and stuff on, right? Or is we have to worry about mutually exclusive, and we have to worry about independent or dependent. So independent, one does not affect the other. Independent is with replacement. Meaning you take something out, you put it back. Or it's a random generated number. Or it's rolling the die. Or it's flipping a coin. Obviously, all of those things, you would start with a fresh set every time. Those are independent. So one has no impact on the second trial.
Independent and dependent both have and?
Yes. If they are dependent, then the occurrence of one does affect the occurrence of the other, and this is without replacement. So you take something out of the box and you don't put it back. You take a piece of paper out of the box with the letters on it and you don't put it back. Now, I altered my set so the second thing I want to get has a different sample space than the first. So this is the same slide, just kidding. In independent, we start with a fresh set every time. Independent, we're going to alter the set, okay? So this one just says, tell whether the events are independent or dependent. A box contains yellow and brown dog treats. You randomly choose one dog treat from the box and you don't replace it. Then you randomly choose a second dog treat. The event A is the first dog treat you get is yellow. The second is that the second dog treat is brown. Are these independent or dependent? Dependent, and why? Because it literally says you do not replace it. There is a different amount of dog treats when you go for the brown than when you went for the yellow. All right, a jar contains red and blue marbles. You randomly choose a marble from the jar, then replace it. Then you randomly choose another marble. First marble you choose red, second you choose blue. Independent or dependent? Independent because you replace it, okay? So conditional probability is your and statements, and the probability that event B occurs given that A has already occurred is what's called a conditional probability. So when you have an and statement and there's dependence, we assume whatever we wanted the first time, we got. So this notation just says, what's the probability of B occurring, assuming A has already occurred? That's what that means, okay? So if I go back to that first one and I say, I don't remember what we were trying to pull for the first time, yellow. Whatever the probability of yellow is the first thing. Then I go to the second thing, and I'm trying to get brown. I assume I got yellow the first time. So when you have an and event, this and that, when we go to do this second thing, we assume we got what we wanted the first time. Yep.
What is that in the middle?
It's just a bar, and it's read as probability B occurs, assuming A had already occurred.
Oh, I thought that was a different.
So that's just what that means. You're assuming A already happened, and you're assuming you got what you wanted from A. So again, independent is an and where they're two separate, okay? Two separate activities, and so I do the probability of the first and the times the probability of the second. Dependent means it's already happened and it's affected my sample space, so I multiply the probability of the first thing happening times the probability of the second thing happening, assuming I got what I wanted the first time. All right, so this one says you spin the spinner shown, which is divided into 8 equal parts. Find the probability that you get red on your first spin and blue on your second spin. So this is an and, right? Red on first and blue on second. We want to identify and or because it's going to start to get mixed in together. Now, if it's an and, we have to figure out, are they independent or dependent? So is a spinner going to go away? What?
Did you just show the conditional probability formula?
So is this spinner spinning a spinner, are those independent or dependent? They're independent. It's not like when you spin it, it goes away, right? So every time you spin it, you're starting with a fresh set, okay? So for the first time, so I'm going to find the probability that you get red, and then I'm going to multiply it times the probability you get blue. What's the probability you get red the first time? There are 1, 2, 3 red spaces, and there are 8 total. So 3 out of 8. Now what's the probability of you getting blue? 2 out of 8. Multiply them, and I'd get 6 out of 64. Or you could simplify and get 3 out of 32. Questions on that one? Yep. So that would be one spin. What's the probability of getting red or blue? Or we add and it's only one event. And is 2 events and we multiply. Yep. All right, example 5. A bowl contains 36 green grapes and 14 purple grapes. You randomly choose a grape, eat it, and randomly choose another grape. Find the probability that both events A and B will occur. Okay, so are these independent or dependent? Dependent. They are dependent because you ate that grape, right? It is no longer part of it. So if it's an and, right, we know that we're doing both, but we have to do probability the first one happens, so the probability of getting a green grape, times the probability of getting a green grape, assuming you already ate a green grape.
Wait, that's dependent?
That's dependent. This is dependent. So what's the probability you get a green grape the first time? 36 out of 50. Now that green grape is gone, so what's the probability of getting the green grape the second time?
35 out of 49.
Good. So not only is our total space reduced by 1, but we assume we got the green grape.
So the first green one is without you eating it?
You haven't eaten it. Yeah, no, you're just picking that first grape. So this would be reduce it, make your life easier. What goes into both 36 and 50? 2, 18, 25. 35, 7 goes in both these, right? 5, 7. At least make them smaller numbers. It's early. 90 over 175. And actually, we could do this. 5 into 25. Make our life, again, easier. 18 over 35. So there is a possibility questions like these are on the portion of your test in which you don't have a calculator. If they are bigger numbers, they will be on the portion of your test in which you do have a calculator. But you will always keep them exact as fractions like that. It's on Thursday, yeah. JP?
How did you know it was dependent?
Because you ate the grape. You changed the sample space. Yep. You're welcome.
This is the last lesson, right?
Yeah. Drawer contains 12 white socks, 8 black socks. You randomly choose one sock. You do not replace it. Then you randomly choose another sock. What's the probability both socks chosen are white? Dependent or independent? Dependent because you do not replace it. So what's the probability that you pick white the first time times the probability you pick white the second time, given you already got a white sock? So what's the probability you pick a white sock the first time? 12 out of 20. What's the probability you get it the second time? 11 out of 19. So this would be 4 3/5, and then 33 over 135. This is dependent, yes. All right, 2, suppose you flip a coin twice. What's the probability you get tails on the first flip and tails on the second flip? Dependent or independent? I just can't do the math. Sorry, don't yell at me. Just kidding. 33. It's very difficult this morning. Great. Yeah, I'm sarcastic, right? 33 out of 95. Yeah. All right. So is for 2 dependent or independent? Independent, right? So what's the probability you pick or get a tails the first time? 1 out of 2. Probability you get it the second time? 1 out of 2. So 1 out of 4. Questions on those? Okay, then, which is funny because we were talking about this at the beginning, like this was on standardized tests, right? Charts. So this kind of like comments. You're going to need to take a picture of this. Take a picture of this. Why is that on in your notes? Most of the rules I would say that we talk about, you don't need to stress too much about when it comes to charts. I think a lot of common sense takes over when it comes to charts. It says the table shows the number of tropical cyclones that formed during the hurricane seasons from 1988 to 2004. Use the table to estimate A, the probability that a future tropical cyclone in the northern hemisphere is a hurricane, and B, the probability that a hurricane's in the northern hemisphere. So 2 separate questions. The first one says the probability that a future tropical cyclone is in the northern hemisphere is a hurricane. So the first thing we want it to be is in the northern hemisphere, which means we're focusing on just that first column. You've already narrowed it down to northern hemisphere. So what's the probability that it's a hurricane? Means I want that 545. So the 545 is going to go over the total, which is 199 plus 398 plus 545. So I'd get 545 over 1,142. Yeah, 1,142. If it asks for it in like percentage, what's the percent? Then you just divide it. It would be 0.477, which would be 47.8%. Okay, it could ask for it in that format. Or the nearest whole percent would be 48%. Just pay attention to how it asks for it. 47.8, unless it asks you to round to the nearest whole percent, which would be 48%. And then B says the probability that the hurricane is in the northern hemisphere. So now we're saying it's a hurricane to start. And what's the probability that of those hurricanes it's in the northern hemisphere? This would be 545 again out of the 545 plus the 215. 760. And then I can reduce this. Divide by 5. This would be 152. 109. Or in decimal or percent form would be 71.7% or 0.72.
So the first one was out of the total in the northern hemisphere.
Right, so the first part said northern hemisphere, second part said hurricane. So it's like a hurricane given that it's in the northern hemisphere. And the second one said it's a hurricane and it's in the northern hemisphere. So you're just grabbing the hurricanes and then what's the probability that's in the northern hemisphere. So the order of the words is super important there. And then this last one, do you have this one? Yeah, okay. You randomly select 2 cards from a standard deck of 52 cards. What's the probability that the first card is not a heart and the second is a heart? And there's 2 different questions here. If A, you replace the first card. So if I replace the first card, this is what? independent. So I want the probability that the first one is not a heart times the probability the second is a heart. So not a heart would be how many? 39 out of 52. Probability it is a heart? 13 out of 52. So this could reduce, this would be 3/4, and this would be 1/4. And I'd get 3/16. 39 over 52. And then B says you don't replace the first card. So we assume, again, probability of not a heart times the probability that it is a heart given not a heart was picked first. So probability of not the heart is still the same. It'd be 39 over 52 or 3/4. But what's the probability of getting a heart assuming you picked a not heart the first time? 13 out of 51. Good. So this actually goes in here. 17 times 13 over 68. So this time our sample space reduced, but what we wanted is not the same. So our top number stayed the same as what it would have been. But the overall sample space got reduced. Questions on anything 8-6 related? So most of this homework, and I'm going to add some in right now. Most of this homework is and. I want to throw in a couple ors just so that you guys can see what it's going to be like because it's going to get mixed in. Okay. So if you